What's going on, besties? This is everything you're going to need to know all in one place when it comes to the ATI TEAS version 7 science portion, more specifically the comprehension of chemistry. Let's get started. So let's delve deeper into the structure of atoms, which are the fundamental building blocks of all matter. So here we have an enlarged depiction of what an atom actually looks like. Although it's not an exact replica of what an atom looks like, it serves our purpose for understanding in this particular moment of the TEAS. So at the heart of an atom lies our nucleus, which contain two different kinds of tiny particles. We have our blue circles, which illustrates our protons, and we have our red circles, which illustrates our neutrons. This nucleus sits centrally in the middle of our atom, and surrounding that nucleus we have these little yellow balls. These little yellow balls actually represent the electrons that circle our nucleus. These electrons move along paths, as I've outlined with these ovals here on your screen, and this indicates that they're always in constant, rapid motion around the nucleus. Electrical charge also plays a critical role in the behavior and structures of atoms. So protons possess a positive charge. Think P in proton. P is positive. Each has a charge of +1, whereas electrons carry a negative charge, each with a charge of -1. Neutrons, in contrast, actually carries no charge at all. So when you think neutral, think N in neutrons, N in neutral. This aligns well with their names. This interaction between positive and negative charges is fundamental to the atomic structure. As we all know, opposites attract each other, which is vital for maintaining that integrity that we see with atoms. Despite our electrons moving at high speeds around the atom, they don't escape into space because of that positively charged proton attracting that negatively charged electron, effectively keeping them within that atom. However, what's good to know is that electrons move too swiftly to actually be pulled into direct contact with those protons. Hence, they orbit around that nucleus rather than colliding inside of it. It's also important to note that the number of protons and electrons are equal, so atoms are electrically neutral particles. Neutrons, despite being uncharged, are significant in the stability of the nucleus. They act as a binding force that helps maintain the nucleus's integrity by mitigating those repulsive forces between the positively charged protons, thus keeping our nucleus together. Another critical aspect of atoms besides electrical charge is their mass. Understanding an atom's mass involves examining the mass contributions of the protons, neutrons, and electrons, with most of that mass being concentrated inside the nucleus. Protons and neutrons are very similar in size and mass, each weighing approximately this tiny little amount in grams. It's a figure so small that it's best expressed by a scientific notation to simplify it. Recognizing the impracticality of such a small number, scientists actually introduced the atomic mass unit as a more manageable measure when we're measuring atoms. Because of this, both protons and neutrons are going to weigh approximately 1 atomic mass unit. In contrast, an electron is significantly lighter than our protons and our neutrons. It only actually weighs about 0.000549 atomic mass units. This minute mass is a mere fraction of that of protons and neutrons. When we're discussing the mass of an atom, we're generally summing up the atomic mass units of our protons and our neutrons, as they substantially contribute to the atom's total mass. Electrons, due to their weight, are typically disregarded whenever we're considering mass calculations of atoms, similar to how you wouldn't account for the weight of a ring or maybe even a necklace when you're weighing yourself. Both of these items are going to be too light to impact the overall measurement significantly. When you examine the periodic table, each element is going to be assigned a specific box that contains two important numbers. Your first number is your atomic number, and your second is your atomic mass. Your atomic number indicates the number of protons that are found in the element. This number is consistent across all atoms of a particular element, distinguishing each element from others. For instance, Hydrogen has an atomic number of 1, indicating that it only has 1 proton, whereas with oxygen, the atomic number is 8, reflecting that there are 8 protons in oxygen. The second number you are going to encounter is your atomic mass, and this tells us how many protons and neutrons we're going to find in an element. A simple mnemonic that I use to remember the differences between atomic mass and atomic number is PAN-MAN. Starting with our first part, PAN, that stands for P is for protons, A is for the atomic number, and N is for the number of protons. And then the second piece with MAN, we know that M stands for our mass number, A stands for add, and N stands for our neutrons. Knowing both the mass number as well as the atomic number of an element allows us to determine the number of neutrons we're going to find in the nucleus of an atom. To find out how many neutrons oxygen has, this can be rearranged into the following formula. Neutrons is equal to mass number minus our atomic number. So if we use this with our oxygen example, we know that our atomic mass is 16 and our atomic number is 8. If we minus those together, it lets us know that we have a total of 8 protons as well as 8 neutrons. So moving on to isotopes, this is a concept in chemistry that's frequently mentioned, but not always easily understood. So let's discuss this with a car analogy. Let's say that we have a fictional car brand called the Citroën, which epitomizes luxury and is celebrated for its distinctive style. For this example, let's imagine that the Citroën are shaped like citrus fruits. The Citroën is going to come in 3 different distinct brands. We're going to have the Citroën C, the Citroën CX, and the Citroën CXL. Each model is available in different colors and features unique options. So the Citroën C might have a basic radio and leather seats, and it's also yellow. The Citroën CX might actually have chrome wheels and a CD player, and it's painted blue. While our luxurious red Citroën CXL is going to feature massaging seats and platinum spinner wheels. The key point here is that despite the variations in colors and features, they're all the same kind of car. They're all Citroëns. Like we talked about before, they all share that same distinctive citrus-like shape. This common characteristic is ultimately what defines the Citroëns, regardless of the specific model or their options. This is very similar to what we see with isotopes. Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. They all have different masses, like the different features in each one of our car models, but chemically they're all the same element. Now let me introduce you to 3 isotopes of carbon. So we're going to be primarily focusing on our nucleus here, represented by our red and our blue dots in the middle. These swirling circles that you see along our atom here actually symbolizes our electrons, but they're not the main concern when we're trying to figure out isotopes. The 3 isotopes that we have is carbon-12, carbon-13, and carbon-14. In carbon-12, if we count these little blue dots, we're going to find that we have 6 protons. And if we count each one of these little red dots, we're going to see that we have 6 neutrons. This is a classic example of what carbon is. Moving on to carbon-13, we still have 6 of our little blue dots, meaning we still have 6 protons, but what's different here is we have an additional red dot. So now we have 7 neutrons. And lastly, with carbon-14, we're seeing the same thing. We still have 6 of our little blue dots, meaning we have 6 protons, but now we have 2 extra dots, right? Now we have 8 neutrons. What do all of these forms have in common when it comes to carbon? Each isotope has 6 protons in its nucleus, which defines it as carbon, just like we saw with our Citroën example. Whether an isotope has 6 or 7 or 8 neutrons, it still has the same characteristics of carbon. These variations don't change the element's fundamental identity. Therefore, what we're dealing with here is we have various forms of carbon isotopes. Different forms of the element have the same number of protons, but they're going to have differing numbers of neutrons. Let's pause to have a better understanding of how these numbers are going to work when we talk about carbon-13 and carbon-14. So starting off with our carbon-12, we know that when we look at the periodic table, this is usually what we're going to see when it comes to carbon. We are going to have an atomic mass of 12 and an atomic number of 6. That 6 lets us know that each one of these atoms has to have 6 protons in order for it to be identified as carbon. This is true for every single one of our examples. The only difference is that our mass changes a little bit as we move down with the additional neutrons. This first example is a classic unit of carbon, right? This example here means that our atomic mass is a little bit more than the standard carbon. Instead of it being 12, it's now 13. So that lets us know there's one additional neutron inside of our atom, just the same way as we see with 14. 14 is just going to be slightly bigger than our 13, and it's just going to let us know that we actually have 2 additional neutrons instead of 1 like we saw with 13. So that is how we determine not only what the element is, but what the weight is depending on how many neutrons are found inside that element. So let's talk about ions. What exactly is an ion? It's a common term in chemistry, so let's break it down a little bit to understand it. An ion is simply an atom or a group of atoms that carries an electrical charge. So exactly how does an atom become an ion? In the nucleus of our atom, we have protons, and they possess a positive charge. And surrounding that nucleus on the outside, we have electrons, which carry a negative charge. Typically, an atom is going to have an equal number of protons and electrons, resulting in no overall charge. However, an atom can become an ion if it gains or loses electrons. So if an atom gains an extra electron, it's going to become more negatively charged than positive, becoming a negatively charged ion. Conversely, if it loses electrons, it will have a more positive charge due to the excess protons, thus becoming a more positively charged ion. This imbalance in the number of protons and electrons results in the atom becoming an ion. Let's start by looking at our sodium atom. In this illustration, you'll notice that our protons are in blue and our electrons are going to be in the outside of our atom circling that nucleus, and they're going to be yellow. While I've omitted neutrons which reside here in our nucleus, they're not crucial in our current discussion since they don't actually carry any kind of charge, and therefore they don't influence the electrical properties of an atom. Typically, a sodium atom contains 11 protons and 11 electrons, resulting in a net charge of 0. This makes sodium atoms neutral. However, what sodium can do is it can lose electrons, and when it does, that dynamic is going to change. For instance, if our sodium loses 1 electron, which is transferring 1 electron from an atom to another, that sodium now has 11 protons and only 10 electrons. This imbalance results in a net positive charge, making the sodium atom an ion with a charge of +1. To indicate that the sodium atom is in a charged state, we denote sodium ions as Na+. In contrast, a neutral sodium atom is going to be noted as just Na. This positively charged ion, or cation as we like to call it, exemplifies what happens when an atom loses electrons and gains a net positive charge. Thus, our Na+ is a prime example of a cation, which is a type of ion that carries a positive charge. A simple and effective way to remember what a cation is we use the catchy mnemonic cations is a positive ion. Think of a cat with paws. To help you recall that cation sounds a lot like cat and ion put together, it helps carry a more positive charge, much like a positive feeling a cat's paws can bring. Now let's consider another example, an atom of oxygen. This illustration shows that we have 8 protons and 8 electrons orbiting around it. The balance between protons and electrons means that oxygen is a neutral atom and has a net charge of 0. So the funny thing about oxygen is it loves to gain and lose electrons. In this scenario, oxygen is actually going to gain 2 electrons. Now with this addition, our protons in the nucleus are going to remain the same, but now we're actually going to have 10 electrons on the outside of our nucleus surrounding it. This surplus of electrons is going to result in that imbalance again, creating a net negative charge due to those 2 extra electrons compared to our protons. This oxygen atom now has a net negative charge of 2-. When we represent this ion with a symbol, we're actually going to indicate O raised to the power of 2 negative to indicate that there is 2 negative charges. In contrast, when we're just talking about a regular oxygen atom that hasn't made any changes, we just denote this with an O. This negatively charged ion is known as an anion. It's a term for ions that have more electrons than they do protons, meaning that they have more of a negative charge. To easily remember that an anion is a negatively charged ion, we use the mnemonic an anion is a negative union. Now I know I said that a little bit funny, but it's just to help with the mnemonic. I want you to picture an onion with negative feelings, characteristics, symbolized by a negative charge like we see with an anion. Let's dive into the concepts of shells, subshells, and orbitals. According to Bohr's atomic model, electrons orbit the nucleus along fixed paths, which he termed shells or energy levels. These shells are going to be denoted by the variable n. So for example, our first shell is going to be denoted by n equals 1. This is also known as our K shell. Our second level is going to be n equals 2. That's going to be our L shell. The next one is going to be n is equal to 3. That is our M shell. And the last one is going to be n is equal to 4. That is our N shell. Now let's discuss subshells. So every shell is divided into subshells or sub-energy levels, denoted by the letters of S, P, D, and F. Here is how the subshells are going to be distributed across different shells. So starting with our first shell or ring or energy level, whatever you want to call it, we have n equals 1. That's our K shell. We're going to see only one subshell, and that's going to be our S subshell. Moving on down to our n equals 2, that's going to be our L shell. We're actually going to see 2 subshells. We're going to see an S and we're going to see a P. Moving down to n equals 3, our M shell, we're going to see 3 subshells. We're going to see an S, a P, and a D subshell. And then lastly, our n equals 4, our very last one, our N shell, is going to have 4 subshells. We're going to have an S, a P, a D, and this time an F. So let's take a closer look at how each one of these shells and subshells affects the orbitals that we see around our nucleus. So what exactly is an orbital? An orbital is a 3-dimensional space within an atom where an electron in a given subshell can be found. So we've already discussed the first part of this concept. We have our shell number and our subshell designation. So we're already very familiar with that. What does all this other stuff mean? So this is how we find the number of electrons depending on what our atom is. So right here, you see here, it says number of electrons. We have shell 1. So we know that shell 1 only has an S subshell. So found within that S subshell, we can only have 2 electrons in that subshell. So that means if we have an atom that has only 1 ring or shell or energy level, whatever you want to call it, they're only going to be able to have a maximum of 2 electrons in that first shell. And if the ATI TEAS ask you how to define the characteristics of an S shell, this is kind of what it's going to look like. It's just a circular sphere. So let's talk about our second shell number, right? That's our second energy level that's completely separate from our first. So as we discussed, we know that we are going to have a subshell of both S and P within this second energy level. And whenever the ATI TEAS asks you, what does it look like? It's going to almost have this dumbbell-like appearance. That is what you're going to see when we're looking at that second energy level. And what's happening here is it's going to have a maximum of 8 electrons found within that second energy level. It's going to have an S and it's going to have a P. Now I want you to remember, this is very important, that this S shell is completely different from our first shell. So if you have an atom that has 2 shells, shell 1 and shell 2, shell 1 is always going to have 2 electrons at most, right? That's the maximum. But our second shell, that subshell is going to have 8 electrons at most. It's going to have its own distinctive S shell that's separate from this first one. So it's going to have 2 there. And then you're going to have this P shell. That's the second subshell that you're going to see when you are on energy level 2. What's important to note that is anytime as we move up in subshells, when we go from S to P to D to F, we're always going to add 4 to that next set of subshells. So in this case, if we had an atom that had 2 energy levels, 2 shells or 2 rings, we're going to see a maximum of 10 electrons total for that atom. So now let's move on to our third shell. So as we know, we have an S, we have a P, and we have a D subshell. And what this kind of looks like, again, the TEAS loves to test you on what these shells look like. It almost looks like a 4-leaf clover, right? So with our first shell, it's more of a circle sphere. Our second shell looks more like a dumbbell, and our third shell kind of looks like a 4-leaf clover. So how many electrons maximum can we have in that third shell? Well, the maximum number we can have is 18. So again, it's going to have an S, a P, and a D shell that are completely separate from shell 1 and shell 2. So its S shell can only have a maximum of 2, its P shell can only have a maximum of 6, and its D shell has a maximum of 10. So that when we add that together, that's how we get our 18 maximum number of electrons. And remember, anytime we're moving up in shells, we're just adding the number 4 in between. Next, we're going to be moving on to shell 4. We're going to have an S, a P, a D, and an F shell. Now, you don't really see what that actually looks like in regards to shell shape like we see with the other ones. It looks completely different depending on the atom. It's going to be all kinds of different configurations, so it's hard to really give you a prime example of what that is going to be. But if you're asked on the test, these are usually the 3 shapes that you're usually going to be tested on. So how many electrons maximum can this fourth shell have? Well, it can have 32. So again, completely separate from anything that's happening within these first 3 levels. Our fourth level is going to have an S subshell of 2, a P subshell of 6, a D subshell of 10, and we're just going to add 4 to get our F subshell of 14. So the maximum number of electrons that this particular shell, energy level, or ring is going to have when it comes to number 4 is going to be 32. So let's break this down of what it's actually going to look like in an atom. So from our example down here, you see we have a magnesium atom, and it has an atomic number of 12. Remember, anytime that we have a neutral atom, it's going to have the same number of protons as it does electrons. So if we have atomic number of 12, we know we have 12 protons, and we should also have 12 electrons. So this is how it is going to look written out. So our first shell is going to have a maximum of 2 electrons in that shell, right? We can't have any more. So 12 minus 2, we're left with 10. So now moving on to our second set of subshells, we have a S and we have a P. So the S is going to have 2 and the P is going to have 6. That means that that subshell for level 2 can only have a maximum of 8. So we're going to see 8 electrons in that second shell. We have 8 plus 2 gives us 10. We're left with 2 more electrons that have to go someplace. So that goes into our third shell. So our third shell, we're only going to have 1 shell. We're going to have an S shell, right? And that's where the final 2 electrons are going to sit. So just to give you kind of an idea of how this is actually broken down, this is what it is going to look like. First shells are going to have 2 because it only has an S subshell. The second shell is going to have 8 because it only has an S and a P subshell. And the last shell is going to have 2 because we can only fit 2, that's what the remainder was, into our last S shell. So to bring this all home, let's examine a model of carbon atoms. So typically it's going to consist of 6 protons, 6 electrons, and 6 neutrons. That is what we're observing right here. So we have our 6 protons and neutrons right here in the middle, and then we have our 6 electrons floating around on the outside in our rings. And as we discussed before, each shell is going to correspond to a distinct energy level and is going to have a maximum capacity of electrons depending on the number of the shell. So carbon has an atomic number of 6, which means we have 6 electrons. So we need to have some place to place those 6 electrons on the outside of our carbon. So our first shell, which is our S shell, our first ring here, our S subshell, I should say, is going to have 2 electrons within that subshell because that S can only hold a maximum of 2. and that's the only subshell that we have in the first energy level of our shell or our ring. So with our second shell, ring, or energy level, whatever you want to call it, we have an additional 4 electrons that we have to place someplace else. We know that based on that second level, that second shell, we can place a maximum of 8 electrons. So we're doing good. We know that the first S of our second layer subshell is going to hold a maximum of 2 electrons, and then we only have 2 left. Those are immediately going to go into the P subshell of our energy level. So this is what a carbon atom would look like and how many shells that they would have, as well as subshells. So during chemical reactions, only the electrons that are in the outermost shells are going to be the ones involved in chemical bonding. So for atoms that possess only 1 shell or energy level, achieving stability requires having at least 2 electrons. For atoms that possess 2 shells for energy levels, they are going to achieve stability only if they have 10 electrons, 2 found within their first shell and the remaining 8 found in their second shell. So let's finish off by examining our last 2 examples. So first we're going to look at helium, which possesses just 1 shell or energy level, and we find that it is complete with 2 electrons. So helium is considered stable. It does not form any naturally occurring compounds. In contrast, hydrogen also only has 1 shell, but that 1 shell contains 1 singular electron, because as we see up here, our atomic number is 1. That means we're only going to have 1 electron. So this actually renders it chemically reactive. A substance's reactivity is a chemical property, best defined as its ability to interact chemically with a second substance. Still, there's only 1 electron found in that S shell. So for it to achieve stability, it needs to gain at least 1 additional electron in that first shell. So how is this achieved? It's achieved through ionic and covalent bonds. So chemical bonds form when 2 or more atoms interact primarily through their outermost shells or energy levels. These interactions often lead to chemical reactions, especially in atoms that do not have 8 electrons in their outermost shells. Atoms may lose, gain, or share electrons to satisfy the octet rule, which states that they prefer to have at least 8 electrons in their valence shell. This octet rule is the driving force behind the formation of various structures like crystals or molecules. This is achieved through 2 main types of bonds: ionic and covalent. Ionic bonds involve the transfer of electrons between atoms. Let's explore how ionic bonds form with an example of sodium and chlorine. Sodium has an atomic number of 11, which means that it has 11 protons and 11 electrons. The distribution of those electrons are as follows. Our first shell is going to have 2, our second shell is going to have 8, and our third shell is going to have 1. Chlorine has an atomic number of 17, meaning that it has 17 protons and 17 electrons. Its electrons are going to be distributed as follows. The first shell is going to have 2, the second shell is going to have 8, and its third shell is going to have 7. To achieve that stable octet, sodium can donate its single outer electron, thus attaining a stable configuration of 8 electrons in its now outermost shell. Chlorine, in turn, accepts that electron, filling its outer shell to reach its desired 8 electrons. This transfer completes both the atom's quest for stability per that octet rule. When that sodium atom relinquishes that electron, it's left with 11 protons, which is positively charged, and now 10 electrons, which are negatively charged. This is going to cause that imbalance, resulting in the creation of a sodium ion that carries more of a positive charge. On the other hand, the chlorine atom receives an electron, bringing its composition to 17 protons and 18 electrons. This excess in electrons is going to form a chloride ion with a negative charge. The newly formed positively charged sodium ion is then attracted to the negatively charged chloride ion, leading to the formation of sodium chloride, also known as table salt. This attraction and resulting bond is known as an ionic bond, characterized by the transfer of electrons that result in the creation of two oppositely charged ions. An easy way that I remember ionic bonds is I take, you give. Ionic bonds form when one atom takes electrons from another, like a transaction where one gives you money and the other one receives it. Next up, we have covalent bonds. So covalent bonds are chemical bonds where two atoms share one or more pairs of electrons within their outer shells. This type of bonding is typical among four major elements found within our body. We have carbon, oxygen, hydrogen, and nitrogen, as they tend to form covalent bonds by sharing electrons. So for example, like we shared before, two hydrogen atoms can form a bond by sharing a pair of electrons. Hydrogen is an exception to that octet rule, which usually states an atom prefers to have at least 8 electrons in its outermost shell. And this is just simply because hydrogen only has 1 electron in its one shell. So let's consider carbon dioxide, CO2, to illustrate a covalent bond. As we know, oxygen has an atomic number of 8, which means it's going to have 8 protons and 8 electrons. 2 in its inner shell and 6 in its outer shell. Thus, it needs 2 more electrons to complete its outer shell. Carbon, on the other hand, has an atomic number of 6, meaning that they have 6 protons and 6 electrons, 2 in its inner shell and 4 in its outer shell. It's going to seek at least 4 additional electrons in order to obtain stability. Here's where that mutual benefit comes to play. One oxygen atom can share 2 of its electrons with the carbon atom, and in return, the carbon atom shares 2 of its electrons with the oxygen atom, satisfying our first oxygen atom. Similarly, the second oxygen atom can also share 2 of its electrons with the carbon atom, and again, that carbon atom is going to reciprocate by sharing 2 of its electrons with our second oxygen atom. This reciprocal sharing results in 3 atoms achieving a stable electron configuration. In this case, by sharing 2 pairs of electrons with each oxygen atom, carbon forms double bonds, which is crucial for chemical structures and reactions. An easy way to remember covalent bonds is sharing is caring. C for covalent, C for caring. You can also think of a combination, co-worker. However it is, it will be easiest for you to remember it. By using sharing is caring, this phrase emphasizes that covalent bonds involve sharing electrons equally or unequally, but always involve some degree of sharing, much like friends share responsibilities or tasks. Lastly, let's talk about the periodic table. Due to its complex structure and breakdown of atomic elements, the periodic table really could be a video all on its own. Thankfully, so far, we've covered most of the information that you're going to need to know in order to pass the TEAS. Here's the additional information that we didn't cover about the periodic table. So what is the difference between periods and groups? Those are 2 terms that you're going to need to know for your test. That periodic table was an essential tool that was developed way back in the 1800s in order to organize chemical elements based on their atomic number and electron configurations. Upon examining our periodic table, you're going to notice that we have 7 horizontal rows. These are known as periods. Each period is going to indicate the number of electron shells that an element is going to possess. For example, elements in the second period are going to have 2 electron shells, while those down here in the 6th period are going to have 6 electron shells. The vertical columns on a periodic table is referred to as groups. Elements within the same group share similar chemical properties. The table features elements in groups numbered 1 all the way to 18. An alternative naming system for these groups uses labels like 1A, 2A. We skip all of our transition metals right here in the center, and it continues on from 3A all the way to 8A, excluding helium. Each element in these groups typically have a number of valence electrons corresponding to its group number. For instance, elements found in group 2A are going to have 2 valence electrons, while those found in group 7A are going to have 7. Most of our transition metals found here in the center are going to have either 1 or 2 valence electrons. So in summary, periods on the periodic table are going to be our horizontal rows, and they are going to indicate the number of electron shells. In contrast, our groups, which are going to be our vertical rows, are going to reflect elements with similar chemical properties. So let's do some practice questions. Question 1 states, what occurs during the formation of an ionic bond? Is it A, electrons are shared equally between atoms? B, electrons are transferred from one atom to another? C, protons are transferred between atoms? Or is it D, neutrons are shared between atoms? And the correct answer is B, electrons are transferred from one atom to another. Ionic bonds form when one atom donates an electron to another, creating ions of opposite charges that are ultimately going to attract. What statement best describes a covalent bond? Is it A, atoms share a pair of electrons? B, atoms transfer electrons to achieve stability? C, atoms gain electrons from another atom? Or D, atoms donate electrons to a shared pool? And the correct answer is A, atoms share a pair of electrons. Remember, with covalent bonds, it's going to ultimately involve them sharing electrons between atoms, typically between nonmetals to fill an outer shell in order for it to achieve stability. The octet rule primarily influences an atom's what? The mass number, the neutron number, the electron configuration, or the proton number? And the correct answer is C, electron configuration. Remember, when it comes to that octet rule, it states that atoms, in order to achieve stability, have to have at least 8 electrons in its valence shell. So it's going to ultimately directly correlate with the electron configuration. What do all elements in the same period on a periodic table have in common? Is it A, they have similar chemical properties? B, they have the same number of electron shells? C, they share the same group number? Or D, they have identical atomic masses? And the correct answer is B, they have the same number of electron shells. Remember, elements that are found in the same period are going to have the same number of electron shells, with each period of the table adding an additional shell as we move from top to bottom. So it's important to note that everything around you is made up of matter. It can exist in different states. It could be solid, it could be liquid, or it could be a gas. These states can change between each other, demonstrated by water. Water vapor represents a gaseous state, while liquid water and ice cubes exemplify a liquid and solid state, respectively. Let's now discuss mass, which refers to the amount of matter contained in an object. For example, a basketball is larger than a tennis ball, so it typically has more mass. We measure the mass of objects in grams or even kilograms using instruments like balances and scales. Volume is the amount of space an object occupies. We typically measure volume in either liters or even milliliters. Graduated cylinders and measuring beakers are common tools for measuring volume of liquids. And then lastly, we have density, and this is defined as the relationship between an object's mass and its volume. For example, let's consider a block of lead and a block of wood that are roughly about the same size, meaning that they have similar volumes. However, that lead is going to be significantly heavier, indicating a greater mass, which results in differing densities between the two. To calculate the object's density, you're going to divide the mass by its volume using the formula density, which is density equals mass divided by volume. If we examine various examples of water, we can find that nearly everything can be classified in one of 3 states: solids, liquids, and gas. These categories are referred to as phases of matter or states of matter. While there are other less common phases like we see with plasma, we're going to focus on the main 3 for now. You're likely familiar with these phases from everyday experiences, but let's explore them from a more scientific or technical perspective, like you're going to be tested on the TEAS. We'll begin with solids. Here we have some examples of solids. We have a block of ice, we have a diamond, and we have a piece of wood. Most of us have an intuitive understanding of what a solid is, but how do we define it scientifically? A solid is defined as having a definite shape and a definite volume. Definite means they are fixed and unchangeable under normal conditions. For For instance, unless subjected to force or damage, a solid like a diamond is going to retain its shape. And speaking of volume, which is the amount of space an object occupies, a solid has a fixed volume as well. Take a cube with dimensions of 1 centimeter on each side. Its volume would be 1 cubic centimeter. Whether you move this cube, roll it around, it doesn't matter, its volume is going to remain unchanged. It is definite. Another key characteristic of solids is that they are incompressible, meaning that we cannot compress them. This means that no matter how much force we apply, that solid is never going to compress into a smaller volume. Here are the fundamental characteristics that define a solid. So we're going to dive a little bit closer into the microscopic view of a solid to better understand its structure. If we were to zoom in on this solid 1 billion times, we're going to see that it consists of tiny little particles, which represent small circles or spheres. As we observe these particles, a few things are going to become very clear. Firstly, they are packed tightly together. Although we can't illustrate it here, these particles are not static. They're constantly vibrating inside of our solid, quivering back and forth. However, these particles are anchored to one spot. They're not going to wander to new locations. They're going to remain fixed in the location they are, always vibrating and always wiggling. This microscopic behavior directly influences the microscopic characteristics of solids. For example, solids have a definite shape like we talked about before, and that's because these particles are fixed in their specific locations. To alter the shape of a solid such as a cube, the particles composing it would need to relocate. So an example of this could be a brick building, for example. The bricks, much like the particles in our solid, don't easily shift to form a new shape because they're fixed into place. And lastly, solids are incompressible because there is minimal space in between these particles to make it possible for them to become packed any more tightly close together, regardless of how much force is applied. So here's everything you're going to need to know about solids. As we work through our examples, we're going to continue to build upon our knowledge of different phases of matter. Let's now discuss liquids. So what characterizes a liquid? Technically, a liquid has an indefinite shape, but it has a definite volume. Let's unpack exactly what that means. A liquid freely flows and conforms to the shape of its container, such as a bottle. That is what is demonstrated by this property. Every time you transfer this liquid to a new container, whether it's a glass, a bottle, or even a beaker, it's going to assume that different kind of shape. This is why we describe the liquid as having an indefinite shape. However, a liquid maintains a definite volume. For example, regardless of the container's shape, if you measure the liquid, the volume remains consistent. Say I have 1 liter in this bottle, and I dump that 1 liter into this bottle. It doesn't matter whether the bottle shapes are different, that liquid volume is going to remain the same. Additionally, liquids are incompressible, which may be surprising for a lot of you. For instance, if we place liquid inside of a syringe and we seal it on the top, no matter how much we try to compress it, we're not able to push that plunger up or down because the liquid simply is so compact, it's incompressible. Therefore, you cannot squeeze a liquid into a smaller volume. So let's take a closer look at what the particles of liquid look like. Unlike the particles that we see in solid, which are tightly packed together, the particles in liquid are close together, but they exhibit much greater movement. In liquid, particles are not fixed, but they move more freely around each other. They swim, they're going to wiggle a little bit past each other. This is actually observed here in our diagram. This mobility of particles is key to understanding why liquid has an indefinite shape. Because these particles can move more freely, they can adapt to new locations easily. This is what allows liquid to pour and take on shapes of their containers. They simply tumble around each other and settle into their new configuration. However, despite this movement, liquids is still incompressible like solids. While the particles in liquid have slightly more freedom compared to their solids, there still isn't a significant amount of space between them in order to allow for that compression like we saw with the syringe. They can't be squished any closer together, which maintains their compressibility. Now we have everything we need to know for liquids. Now let's discuss our final phase of matter, gas. Gases might seem a bit peculiar because most of them are invisible like air, and only a few gases are actually visible to the human eye. Sometimes people might think that gases actually aren't matter, but in contrast, they actually are. Regarding their specific characteristics, gases have both an indefinite shape and an indefinite volume. Like liquids, gases' shapes change to fit whatever container they're in, which is why their shapes are considered indefinite. However, gas volumes also change. For instance, the gas currently occupies this bottle, but if I was to remove the top from this bottle and allow some of that gas out, that gas is going to expand and fill a larger volume. Gases can expand or contract to fill any available space, making their volumes indefinite as well. Unlike their solid and liquid counterparts, gases are compressible. If we were to take that same syringe from before and get all of the water out of it and fill it up with just gas, I'm going to put the plunger back on top, we're going to see that as I push the plunger down, look at that, I'm able to compress the gas inside of this syringe. This compressibility is a distinctive property to gases, differentiating them from all other states of matter. So let's take an even closer look at gas. Zooming in, we can see that particles are really spaced out, and they're constantly in rapid motion, zipping around at high speed. Gases, like liquids, have an indefinite shape because their particles are free to move around to any new location. They also possess an indefinite volume, meaning that they can expand and they can contract depending on the available space. This ability to change volume is due to the particles being really far apart from one another and them being in constant motion. When given more space, the particles are going to spread farther apart. However, if we compress that space and give them a smaller space, they're going to ultimately draw closer together. This explains why solids and liquids have a definite volume. Their particles are packed closely together and they don't separate or spread apart significantly like we see with gas. This brings us to the concept of compressibility when it comes to gases. Gases are compressible because their particles are so spaced out, leaving a lot of room in between them, like we saw with our syringe example. Because there's so much space in between our gas here in the syringe, we are able to compress them into a smaller volume. And there you have it. Here is our completed breakdown of all of the different states of matter that you're going to need to know for the ATI TEAS. So let's explore how temperature and pressure is going to influence changes of our states of matter using water as our example. To begin, let's consider a beaker containing a big block of ice attached to a thermometer. As we start heating up that ice, increasing our temperature, the temperature recorded by the thermometer is going to increase until it reaches a critical point. At this stage, our ice is going to start transforming into water. On a microscopic level, imagine numerous little ice particles tightly packed together in their solid form. Each of them are vibrating in place. As heat is applied, we're going to see an increase in kinetic energy, causing them to vibrate even faster. Continued heat is going to allow these particles to overcome the force holding them together, enabling to start to move more freely and transition into a liquid state. What's really interesting is that during the transition from ice to water, the temperature remains a constant 0 degrees Celsius. This temperature is known as our melting point. For ice, this melting point reflects the minimal amount of energy required to weaken and break apart those intermolecular forces binding the particles together. Once all of our ice has melted, the temperature of the water is going to remain at 0 degrees Celsius until the ice has completely transitioned into water. Any additional heat supplied during this phase is used to break the remaining intermolecular bonds. After all the ice is melted, and if the heating continues, the water temperature begins to rise again. When the temperature reaches 100 degrees Celsius, the water starts to boil. Boiling is a phenomenon that occurs throughout the liquid, signifying the transition from liquid into gas once it reaches the boiling point. At this stage, the particles already moving freely gain sufficient kinetic energy to overcome their intermolecular bonds and enter into a more gaseous state completely. Next up, let's consider how pressure affects the state of matter, using gas in a bottle as an example. If we compress the gas by pushing down our plunger, reducing the volume, the particles are going to be forced to move closer together. If the temperature within the system is always kept low, the increased pressure and reduced volume causes those gas particles to attract to each other strongly enough that it's going to start to transition into a liquid. This process demonstrates how increasing pressure, particularly in combination with lower temperatures, can liquefy gases. In addition to knowing that matter exists in these three states, solid, liquids, and gases, you also need to know the 6 transformations that can take place between them. Let's discuss each one of these in detail. So starting with melting. Melting is the process where a solid becomes a liquid when it absorbs heat. So an example of this is like we talked about before with ice melting into water. This is the most common example. As the ice absorbs heat from its surroundings, its molecules increase its kinetic energy, weakening those intermolecular forces that have kept them fixed in place, allowing them to move more freely and transition into a liquid state. Freezing, on the other hand, is defined as the process where liquid turns into a solid state. This occurs when the liquid loses heat, causing those molecules to slow down and rearrange into a fixed solid structure. A common example of this is when water freezes into ice. When the temperature of water drops below 0 degrees Celsius or 32 degrees Fahrenheit, the movement of water molecules slows down sufficiently so that they can crystallize into ice. Next up, we have condensation, and condensation is the transformation of a gas into a liquid. This happens when a vapor loses energy and its molecules slow down enough to stick together, forming a liquid. A common example of this is when water vapor condenses on a cold glass. That cold surface is going to cool the water vapor that's found in the air, reducing its energy and converting it back into liquid droplets. And then we have evaporation. So evaporation is the process of a liquid turning into a vapor or a gas at a temperature below its boiling point. It typically occurs at the surface of a liquid. So an example of this could be water evaporating on a pond. Even on a cool day, water molecules at the surface can gain enough energy from the sun to escape into the air as vapor. And our last 2 examples is sublimation and deposition. So when we're talking about sublimation, we're talking about the direct transition from a solid into a gas, bypassing the liquid state altogether. This occurs under specific conditions when it comes to temperature and pressure. A common example of seeing this is dry ice, which is solid carbon dioxide ultimately sublimating. At room temperature, dry ice turns directly into carbon dioxide gas, rather than first melting into a liquid. And then lastly, we have deposition, which is the direct transition from a gas into a solid state, completely again skipping that liquid phase. This occurs when those gas molecules lose energy very, very quickly. So a common example of this could be frost forming on your window. So on a cold winter day, that water vapor that's going to be found in the air can directly deposit onto the cold window pane as ice without ever having to become a liquid first. So let's do some practice questions. What is the process called when a solid turns directly into a gas? Is it condensation, deposition, sublimation, or evaporation? And the correct answer is C, sublimation. Remember, sublimation is the process where a solid transitions directly into a gas without passing through that liquid phase. This is observed with things like dry ice, like we talked about before, where it turns directly into carbon dioxide gas when it's exposed to room air temperatures. What state of matter has a definite volume but not a definite shape? Is it solid, liquid, gas, or plasma? And the correct answer is B, liquid. Remember, liquid has a definite volume, meaning that they occupy a set amount of space, but they do not have a definite shape. Instead, they take the shape of the container that they're in. Which of the following is not a characteristic of a solid? Is it A, a fixed volume, B, a fixed shape, C, the ability to flow, or D, not being compressible? And the correct answer is C, its ability to flow. Remember, solids have a fixed shape and they have a fixed volume. But unlike liquid and gases, they don't flow. They just kind of vibrate in place in their fixed positions. What is the term for the temperature at which a liquid turns into a gas? Is it the freezing point, boiling point, melting point, or sublimation point? And the correct answer is B, the boiling point. The boiling point is the temperature at which liquid changes into a gas, occurring throughout the bulk of the liquid, not just on the surface as we see with evaporation. So let's delve a little deeper into what chemical reactions are, because they're incredibly significant. The very existence of you and I hinges on chemical reactions taking place. As we speak, our body is the site of innumerable chemical reactions occurring every moment. Life, as we understand it, and indeed the universe itself, would not be possible without these reactions. So what exactly is a chemical reaction? Well, they are one or more substances known as reactants that are transformed into different substances called products. They occur whenever bonds between atoms and molecules are created or severed. So what exactly does that entail? So here on the left-hand side of our equation, we have reactants. These are the molecules that will participate in the chemical reaction. Think of them as like the ingredients of a cake. And then we have an arrow that moves our reactants into our product. And then we have the product. The product is going to be the result of our chemical reaction. Think about it being the cake that was mixed up and cooked from our ingredients. So let's look at a real-life example that you're going to encounter on the TEAS when it comes to the molecules and how they create chemical reactions. So this particular reaction is one of the most essential chemical reactions. Without it, life as we know it, including the existence of water, would be at risk. In this case, the reactants are molecular hydrogen and molecular oxygen. The term molecular hydrogen refers to the typical form that hydrogen takes when it's alone, consisting of two hydrogen atoms bonded together, visible as a pair of hydrogen atoms. In order for the reaction to proceed, it isn't enough to just have one molecule of hydrogen and one molecule of oxygen. It requires two molecules of hydrogen in order for this reaction to take place. This means that we're dealing with 4 hydrogen atoms in total, indicating that we're dealing with 2 molecules of molecular hydrogen. The subscript 2, like we see here at the bottom of our hydrogen, lets us know that our molecule contains 2 hydrogen atoms, while the coefficient 2, right here before our H2, indicates the presence of 2 such molecules for the reaction to occur against each molecule of molecular oxygen. Similarly, molecular oxygen is made up of 2 oxygen atoms, as noted by the subscript 2. The reaction requires some energy to get started, but once the conditions are right, the reactivity between molecular oxygen and molecular hydrogen is high. In fact, it's so high that it's even utilized in rocket fuel. As a result of this reaction, you will end up with 2 molecules of water. This is a product as we see illustrated here. It's important to note that in this process, no atoms are created or destroyed. So if we take a look at our equation, we know that we have 4 hydrogen molecules and we have 2 oxygen molecules. So if we were to count our products on the other side, we're going to see that we have the exact same number of atoms. We've got 1, 2 oxygen, 1, 2 oxygen here. We've got 1, 2, 3, 4 hydrogen here, and 1, 2, 3, 4 hydrogen here. So this reaction not only rearranges atoms, but it also releases energy. While I'm simplifying the details, it's sufficient to say that some energy is needed to initiate the reaction. But once it's started, it releases a significant amount of energy, making it highly exothermic. This is a reaction that, with just a small initial input of energy, will release a considerable amount of energy in the process. So you may be wondering, and I certainly did as well when I first encountered the topic of reactions, is how exactly does this process unfold? Is there a sense of order as to how the molecules are somehow predestined to combine? The reality of this is it's quite the opposite. Chemistry, in essence, is a rather chaotic affair. Molecules are constantly in motion, propelled by their energy. This motion becomes even more vigorous when additional energy is introduced, causing them to collide even more forcefully. It's through these collisions occurring at just the right manner, the old bonds are going to be broken and new bonds are going to be formed. This spontaneous and somewhat random interaction between the molecules is what drives the complexity of chemical reactions. Now let's explore a concept related to this reaction. While the process strongly favors the formation of water, reversing it is going to be exceptionally difficult. Typically, we classify these kinds of reactions as irreversible, not because reversibility is impossible, but because it's highly improbable under normal conditions. The notation used to describe this reaction, with the arrow only pointing in one direction, suggests that this kind of chemical equation is irreversible. So let's take a closer look at an example that has a reversible reaction. So here's an example of a reversible reaction involving a bicarbonate ion. The term ion refers to any molecule or atom with a net charge due to an imbalance of its electrons and its protons. In this case, we're dealing with a bicarbonate ion and a hydrogen ion, each carrying a charge. Our bicarbonate ion has a negative charge, and our hydrogen ion has a positive charge, making them both ions. The reactants feature a bicarbonate ion interacting with a hydrogen ion, which is essentially a hydrogen atom that has lost its electron. This process can lead to the formation of carbonic acid, demonstrated by the hydrogen ion attaching to one of the oxygen atoms of the bicarbonate. This reaction is an equilibrium reaction, meaning that it can proceed in both directions within the solution, shifting back and forth. The direction of the reaction is going to depend on the concentration of reactants and products. By adding more reactants, it's going to push the reaction forward. However, when we add more products, it's going to push the reaction backwards. In a real-world scenario, this dynamic allows the reaction to continuously fluctuate between the reactions and the products, with the balance of reversible reactions being influenced by the relative amount of substances that are present. Thus, the direction of the reaction is determined based on the likelihood of interaction or dissociation with its surroundings. To give you an idea of its significance, you might wonder if carbonic acid is merely just a series of random characters that I've mentioned. In reality, carbonic acid is a crucial compound, a term that we use when it comprises of two or more elements. It's not only significant in biological systems, but also in our environment. For instance, it plays a key role in carbonated beverages. That fizz that you see is actually carbonic acid breaking down into carbon dioxide. Beyond its presence in our drinks, carbonic acid is vital to how our bodies manage excess carbon dioxide in the bloodstream. It also plays a role in how oceans absorb carbon dioxide from the atmosphere. Therefore, when you're studying chemistry, especially when it comes to biological perspectives, these concepts are not merely academic curiosities. They have direct implications on our daily lives, affecting our health and the environment around us. Now that we have a general idea of how chemical reactions work, let's examine 5 different kinds of chemical reactions that you're going to see on the ATI TEAS. On this slide, we have the 5 most common chemical reactions that you're going to see on your exam. Let's break each one of these down so that we can understand them in order to ace them. So first up, we have synthesis or combination reactions. This is when 2 distinct reactants come together to create a single product. The subscript 2, like we see here with our hydrogen and our chlorine atoms, indicate that these are diamotic molecules, meaning that these elements naturally pair up to form molecules consisting of 2 atoms. So when we think combination, we think of combining atoms. That's the big key takeaway I want you to take from this. And this is molecularly what is happening with our atoms. So you can see here we have A plus B, which would be our reactants, is going to ultimately make a product of those 2 atoms combined together. So our first one we have here is we have hydrogen, and this is what it would look like. It would be 2 hydrogen atoms connected together. Then we have chlorine, and again, because of that subscript 2, it's telling us that we have 2 chlorine atoms that are combined together. And what we see is that when we combine them together, we're going to have a chlorine atom attached to a hydrogen atom and another chlorine atom attached to another hydrogen atom. So that's where we get our coefficient 2. It's just telling us that our product created 2 hydrogens and 2 chlorine atoms. They just happen to be connected separately. Conversely, when we flip the script and reverse the process of a synthesis reaction, we're going to end up with a decomposition reaction. And this is characterized by a single reactant splitting into several products, showcasing the versatility of chemical reactions. So like we said, we're going to have a single reactant that's going to be combined, and it's ultimately going to split into individual atoms. So using our previous example, if we had two hydrogen chlorine atoms like we see here, ultimately our product is going to split these atoms apart, and they're going to go back into diamotic molecules, meaning that we're going to have two hydrogen and we're going to have two chlorine atoms. There are a lot of common diamotic molecules that you are going to see. These are the most common ones that you should be familiar with, as these occur naturally within nature and come in pairs. So this reaction is known as a single replacement or single displacement reaction. In this scenario, the reactants consist of one element or compound which react to form a new element or compound. Essentially what we're doing is we're exchanging one metal for another in the reactant to generate two new products. So as you can see from our example, we have one element here that's going to be combined with one of our compounds. On the other side, on our product side, we're going to see that we're going to have a new compound and an element that is now by itself. So how exactly is this broken down? As you can see from our example, we have one iron molecule here on our reactant side, and we're going to be combining it with a copper sulfate molecule on our reactant side. So our iron molecule is going to be by itself, and then our copper and our sulfate are going to be together. This is what it's going to look like when it's chemically structured. So what you're going to see is we're going to switch one metal molecule for another in order to create a product. So on this side, our metals are iron and we have copper. So as we move over to our product side, you're going to see that that iron is now attached to our sulfate molecule, making ferrous sulfate, also known as iron salt. And now our copper molecule is all by itself. So that's what we're looking at when we're talking about single displacement. We're switching the metals and we're going to create a new compound and a new element by itself. So a double replacement or double displacement reaction operates on a principle similar to how we saw with our single displacement reaction, with the key difference being that both reactants are going to be compounds. These reactants are going to react together to create two new distinct compounds. So here's a memory trick for you. I want you to visualize the inner elements combining together and the outer elements combining together in order to form new compounds. Alternatively, you can also see this as them swapping metals or other elements in exchange for generating new compounds. So let's take a closer look at our example. So A and B is one compound, and C and D is another compound. And as they move over into the product side, A and D is now going to be together, and B and C are now going to be together. So down here we have our first element. This is silver nitrate. Our next element is going to be potassium chloride. So if we look down here, this is kind of what our element is going to look like structurally. We're going to have our silver here, and then we're going to have our nitrate combined with our silver. And then for our next product, we have our potassium here, and our chloride is also going to be combined with our potassium. So now what we want to do is we want to mix it up, right? So we are going to start exchanging those metals, or we're going to combine our inner elements with our outer elements. So when these elements mix together, they form new compounds. So here, our silver element has now combined with our chloride element, and it's made silver chloride. And on the other end of our product, we have our potassium element has now combined with our nitrate element, and that has made potassium nitrate. So finally, we're going to talk about combustion reactions characterized by the burning process. So up here we have the general formula of what a combustion reaction looks like, and down here we have a couple examples of what that could be. Our initial reaction that we see here could either be carbon and hydrogen, or it could be carbon, hydrogen, and oxygen. So here is another memory trick, so listen up. A definitive sign of a combustion reaction is there's going to be presence of an oxygen molecule, as we see here with our second reactant. And it's going to invariably lead to a product of carbon dioxide and water. The outcome is going to remain consistent across all combustion reactions. So as long as you see that second reaction as oxygen and you see your products as being carbon dioxide and water, you know you have a combustion reaction. The goal of balancing chemical equations is to ensure that the number of atoms for each element is identical on both sides of the equation. My key tip here is to start by balancing all other elements other than hydrogen and oxygen. You want to save those two for last. So let's begin by tackling how I balance chemical equations. We're going to start by listing all of our elements for our reactants and all of our elements for our products on each side of the equation. It's really important to maintain the same order on each side because it helps maintaining that equation and that balance so much easier. A useful strategy is to make sure that you keep all polyatomic atoms as they appear on both sides of the equation together. So as you see here, we have OH and we have OH. It just makes it easier and it makes simplifying this process a whole lot better. Now let's examine the reactants to determine the quantity of each element. So if we take a look, we see that we have one Ba element, we have two Cl elements by the subscript of 2 is letting us know. We have one Na element, and we have one OH element. So we want to do the same thing that we did on the reactant side with the product side. So over here we have one Ba element, we have two OH elements because we can see that we have a subscript of 2. We have one Na element and one Cl element. So next up we want to identify which elements are going to need to be balanced. So we're just going to compare the elements on one side with the elements on the other side, starting with our Ba element. We can see that we have 1 on both sides of our equation, so we are good there. There's nothing that we need to do. But look here, a Cl element has 2 on the reactant side and 1 on the product side, so we're going to have to balance that. Our Na element looks good. We have 1 on both sides, but our OH element is another problem, right? We have 2 on the product side and 1 on the reactant side. So as we are looking to balance these chemical equations, make sure we keep the hydrogen and the oxygen for last. So this OH element is going to be the very last thing that we balance. We're going to start with our Cl element. So in order to balance chlorine on our product side, we're going to add the coefficient 2 before our NaCl. Remember, anytime we have polyatomic atoms, we want to keep them together. So now we're going to add up all of our elements on each side of the equation again. We didn't touch anything on the reaction side, so we can just pull our numbers over again since we didn't do anything over there. However, we do need to add up everything on the product side again to make sure we have the right numbers. So we have one Ba element, we still have 2 OH elements. Now, this is the big key. Whenever we add a coefficient to the start of a polyatomic atom, we need to make sure that we are combining that coefficient to everything that's inside that atom. That means that we're going to have 2 Na elements and we're going to have 2 C elements because there is a coefficient before that compound. So in this case, I'm going to put that I now have 2 Cl elements and I have 2 Na elements. And then we move on to looking at how many elements we have on each side in order to see if we've balanced our equation. So as we take a closer look, we can see we have one Ba element on both sides, so that's still equal. Now we have evened out our Cl element. We have 2 on both sides. But look here, we have 1 sodium on our reactant side, and we have 2 on our product side, so we're going to need to balance that out. And of course, we still have an issue with the balance of our OH, but we always want to save that one for last whenever we see hydrogen or oxygen. So this means the next element that we're going to need to balance is going to be our Na element. So how do we do this? We know that we have 2 on the product side, and we have 1 on the reactant side, so what are we going to do? We're going to add the coefficient 2 before our polyatomic atom of NaOH. So now we're going to tally everything up together again. So on our reactant side, we have 1 BH, 2 Cl. We now have 2 Na, because remember, anytime we add a coefficient, we are going to multiply that coefficient by each individual element inside our polyatomic atom. So now we know we have 2, and we also have 2 OH elements. Nothing changed on our product side, so we're just going to pull those numbers over again like we did the last time. So now let's tally everything up. We have 1 Ba on both sides of our equation. We have 2 Cl's on both sides of our equation. We have 2 Na molecules on both sides of our equation. And we have 2 OH molecules on both sides of our equation. So because we saved our oxygen and our hydrogen for last, they ultimately ended up balancing themselves out as we were balancing out the other elements. So now we have a completed chemical reaction that is balanced on both sides. Let's take a look at one more example. So just like we did before, we want to make sure that we list out our elements on both sides of our equation. As we can see here, we only have carbon, hydrogen, and oxygen on both sides. Now we're going to start tallying up. So we've got 2 carbons here, we've got 4 hydrogens here, and we have 2 oxygens here. On the product side, we have 1 carbon atom, we've got 2 oxygen atoms, we have 2 hydrogen atoms, but oh, look here, we have an extra oxygen atom, so we need to make sure that we account for that. So we have 2 here, and we have 1 here. Adding them together, we have a total of 3 oxygen atoms on our product side. And as always, we need to tally them up and see if they match. So on the reactant side, we have 2 carbon, and we only have 1 on our product side. Hydrogen, we have 4 on our reactant side and 2 on our product side. And oxygen, we have 2 on our reactant side, and we have 3 on our product side. Well, this is a mess. We're going to have to balance everything out. So we know we're going to start with our carbon atom, but what am I supposed to do now that I have hydrogen and oxygen? Weren't we supposed to save them for last? Yes. Here is the strategy. My strategy involves addressing hydrogen second to last and oxygen very last, because this approach significantly streamlines the process, as oxygen will naturally usually balance itself out towards the end. So starting with our carbon, we have 2 on our reactant side and we have 1 on our product side. So that means that I'm going to need to add a coefficient to the product side in order to equal it out. What is that coefficient? We're going to add 2. That way it'll give us 2 carbon on one side and 2 carbon on the other side. Let's tally up and see what we have now. So nothing changed on our reactant side, so I'm just going to go ahead and pull the numbers over to save us some time. So now we're going to tally everything up on the product side. So as we can see here, we have the coefficient that we added before our CO2. So anytime we have a polyatomic number that we add a coefficient to, you want to make sure that you are multiplying 2 by everything found inside that element. So starting with our carbon, we know that we have 2 carbon, and we have a subscript of 2 for our oxygen. We're going to multiply that by our coefficient of 2, giving us 4. Over here we have 2 hydrogen, and of course we have this lone oxygen. So we're just going to add these 2 numbers together. So 4 plus 1 is going to give us the number 5, meaning that we have 5 oxygen atoms on the product side of our equation. So now we're going to balance them out. We're going to look and we see that we have carbon on both sides of 2, so we're good there. On our hydrogen, we have 4 on the reactant side and 2 on the product side. And for oxygen, we have 2 on the reactant side and 5 on the product side. So we know that now we're going to have to balance out our hydrogen and our oxygen. But remember, we're going to do hydrogen first. Hydrogen is always second to last. And oxygen is going to be the very last thing that we touch. So we know we have 4 hydrogen on our reactant side and we have less on our product side. So we're going to need to add a coefficient to our product side. So in order for me to get 4 molecules of hydrogen on our product side, I'm going to add the coefficient of 2. Because I have a hydrogen with a subscript of 2, I know that if I multiply that by a coefficient of 2, it's going to give me 4. So now we're going to tally everything up again. So again, we haven't touched anything on the reaction side, so I'm going to go ahead and just pull over our numbers from before because I know they are still accurate. Now I need to count everything on the product side to see how we're doing. So I have 2 carbon, I have 4 oxygen. Now again, I added this coefficient of 2, so we're going to multiply everything by 2. So now I have 4 hydrogen, and now I have 2 extra oxygen here because I have the coefficient of 2 that's also affecting my oxygen. So 4 plus 2 is going to give me a total of 6 oxygen molecules. So let's see if we're balanced. I have 2 carbon on each side. I have 4 hydrogen on each side. Oh, but look here, I have 2 oxygen on my reactant side, and I have 6 oxygen on my product side. That means I'm going to have to add a coefficient somewhere over here on my reactant side in order to balance out this equation. So now I know I need to get 6 oxygens onto my reactant side in order to balance out this equation. So because I have a subscript of 2, I need to multiply that by my coefficient in order to get 6. So what can I multiply 2 by in order to get 6? You got it. I'm going to multiply it by 3. So I'm going to add the 3 coefficient in front of my oxygen molecule on my reactant side. And now we're going to tally them all up again. So over here I have 2 carbon, I have 4 hydrogen, and now I've got 6 oxygen because 3 multiplied by 2 gives me 6. I didn't touch anything over on my product side, so I can just pull over my numbers like you see that I'm doing here. And now we're going to tally everything up. So I've got 2 carbon on both sides of my equation. I've got 4 hydrogen on both sides of my equation. And now I have 6 oxygens on both sides of my equation. Now I have a balanced equation. So let's talk about moles. Now when I mention a mole, I'm not referring to that charming, cute little creature that you see on TV. Instead, I'm talking about the concept that is fundamental in chemistry. A mole is a term used to denote a specific quantity of items. Think of it like a dozen, meaning that we have 12 items. However, a mole represents a much larger number. It's actually 602 hexillion items to be more precise. This number is written as 6.022 times 10 to the 23rd power. This is often referred to as Avogadro's number. Just like there are 12 items in a dozen, there is 602 hexillion items in a mole. A common point of confusion about moles is the assumption that it's shorthand for molecule, leading to a lot of misunderstandings. When I say mole, I'm not alluding to molecules, but to a collection of 602 hexillion items. This clarification is crucial since, like a dozen, a mole can apply to any group of items, not just molecules. So what makes Avogadro's number unique is that it represents a quantity of an item. Let's look at an example of carbon atoms found in precisely 12 grams. A single carbon atom contains 6 protons and 6 neutrons, and it has a mass of 12 atomic mass units, also known as AMUs. So a mole corresponds to the quantity of carbon atoms whose combined weight equals this figure, but it's expressed in grams. Essentially, a mole serves as a bridge connecting atomic mass units to grams. Let's take a look at another complex example, a water molecule. We know that it has a total mass of 18 atomic units. 16 of those come from our oxygen, and 1 atomic unit comes from each of the 2 hydrogen atoms, based on their average masses, as we can see on the periodic table. Therefore, by definition, a mole of water molecules has a mass of 18 grams. So in order to calculate the molar mass of a substance, you're simply going to sum up the atomic masses of all of the atoms that are present in the molecule. So this is how we are going to determine how to find moles. So here we have the question: what is the molar mass of vitamin C? This is what I do. I start off by creating my parentheses and my addition in between each element that we're going to find in this particular unit. So I start by looking at my subscripts and I start putting in my numbers. So I have 6 carbon, I have 8 hydrogen, and I have 6 oxygen. Next, I want to multiply each individual element by its atomic mass. So as you can see here, carbon has an atomic mass of 12, hydrogen has an atomic mass of 1, and oxygen has an atomic mass of 16. Next, we want to perform the multiplication found inside our parentheses. So we know that 6 times 12 is going to give us 72, 8 times 1 is going to give us 8, and 6 times 16 is going to give us 96. And the very last thing we want to do is add all of these numbers together. So 72 plus 8 is going to give me 80, plus 96 is going to give me a total of 176. This means that for vitamin C, our molar mass is going to be 176 grams per mole. Next, let's explore the variables that influence the speed of chemical reactions, including temperature, concentration of pressure, surface area, and the role of catalysts in either promoting or not affecting the reaction. Before delving deep into how these factors impact reaction speed, it's essential to grasp the foundational theory that explains reactions known as collision theory. So this principle asserts that for particles to react, they must collide with sufficient energy, also known as activation energy. Collisions with energy below this threshold results in no reaction. The particles simply just bounce off each other. Therefore, when considering a reaction involving countless particles, the reaction rate at any given moment hinges on two key factors. Firstly, we have the energy level of the particles. When you think about it, higher energy increases the likelihood of surpassing the required activation energy during collisions. And then secondly, we have the frequency of collisions. So the more frequent these collisions take place, the higher the probability of successful reaction, even if not all collisions meet that activation energy. When we analyze how these four factors, temperature, concentration of pressure, surface area, and catalyst present, are ultimately going to affect reaction rates, it's crucial to consider their impact to the energy of the particles and the frequency of collisions. Enhancing either aspect is going to lead to an increase in the rate of reactions by boosting the number of successful collisions. So beginning with temperature, as it rises within a reaction, the particles are going to obtain additional energy. This increase in energy is going to cause them to move faster, and it's ultimately going to lead to more frequent collisions. Additionally, each collision is going to happen with greater force and energy, enhancing the likelihood of them surpassing that activation energy threshold. This is ultimately going to result in a greater chance of successful collisions, thereby accelerating the reaction rate. And then we have concentration and pressure. They're often grouped together as they both relate to the number of particles within a given volume. The term concentration typically applies to solutions, while pressure is associated with gases. Increasing either our concentration or our pressure is going to result in a higher density of particles per unit of volume. This is going to lead to more frequent collisions and ultimately result in an accelerated reaction rate. Similar to concentration and pressure, an increased surface area can also boost the reaction rate. For instance, if we aim to react 3 grams of magnesium to an acid, we could use a solid block of magnesium, smaller magnesium chunks, or even a powder in order to make that happen. Given that all forms have the same mass and same volume, the powdered magnesium is going to offer the greatest surface area to volume ratio. This increase in surface area is going to allow for more extensive contact with the acid, facilitating more frequent collisions between the reactants. And then of course, this heightened collision frequency is going to lead to an accelerated reaction rate. The final element to discuss is the role of a catalyst. Catalysts are agents that expedite chemical reactions without being consumed in the process, which is why they do not appear in the reaction equation as neither a reactant or a product. To grasp their function, consider reaction profile illustrating the energy change of chemicals during a reaction. The gap between our energy level of the reactant and the peak of the curve represents activation energy. This is the minimum amount of energy required for a collision to result in a successful reaction. A catalyst is going to reduce the activation energy by offering an alternative pathway for the reaction, thereby increasing the likelihood of successful collisions. The term catalyst encompasses a wide variety of substances that can facilitate reactions under different conditions. Transition metals like cobalt and nickel are among the most prevalent catalysts. In the field of biology, catalysts are known as enzymes, which are essentially catalysts produced by living organisms, playing a crucial role in the various biochemical reactions. Now that we have a better understanding of the reaction profile, let's consider the differences between exothermic and endothermic reactions. A fundamental principle here is that different chemicals encapsulate varying amounts of energy within their bonds. Take, for instance, the reaction of methane when it reacts with oxygen to produce carbon dioxide and water. Each molecule that's involved in this process is going to possess a unique energy level, contributing to their respective chemical energy stores. What's critical is comparing the total energy contained by the reactants to that of the product. In the given example, the product will have less energy than the reactants, a difference that can be visualized as a reaction profile on the y-axis, representing the total molar energy, and the x-axis charting the reaction's progression. Reactants are positioned to the left, and products are positioned to the right, with products placed lower to indicate the reduced energy levels. The loss of energy by the chemicals implies an equivalent energy release to the surroundings, adhering to the principle of energy cannot be created or destroyed, only transferred. Heat is going to be the most frequent form of energy exchange in such scenarios. In a sealed environment, this reaction would only manifest as measurable temperature rises, attributing to the release of heat energy. These kind of reactions are termed as exothermic, characterized by their energy transfer to the surrounding, predominantly as heat. When you think of exothermic, I want you to think of the word exit, which means that heat is exiting during the reaction. So common examples that you will see with exothermic reactions are combustion reactions, and this is where fuels combust in oxygen. This serves as the prime example of exothermic processes, but there's also additional processes like neutralization, like you see with your acids and your bases, as well as oxidation kinds of reactions. Conversely, an endothermic reaction is going to be the complete opposite of an exothermic reaction. These reactions absorb heat energy from their surroundings. If we illustrate this process with our reaction profile, we maintain our reactants here on the left and our products here on the right like we did before. However, this time the product is depicted higher on our graph because it contains more energy than the reactants. This elevation is marked as the energy is being absorbed, distinguishing it from the energy that was being released. When you think of endothermic, I want you to think of enter, En and endo, En and enter. This means that the heat is entering or being absorbed during the reaction. Primary examples of endothermic reactions could be the cooking of an egg. As the temperature increases when the egg is being cooked, the heat is being absorbed from the pan into the egg, making this an endothermic reaction. Most other common reactions you might see is photosynthesis reactions as well as liquid evaporation. Earlier in this video, we talked about reversible and irreversible reactions. Specifically, reversible reactions taking place are capable of achieving what is termed as equilibrium. An equilibrium reaction is characterized by the forward reaction occurring at the exact same rate as the reverse reaction. In instances where a reaction is reversible, we can attain equilibrium. This state is represented by a specific symbol, rather than an arrow within a chemical equation. So what exactly does equilibrium entail? So initially, the forward reaction proceeds more rapidly than the reverse reaction due to the higher concentration of reactant particles compared to the product particles at the start. However, as the concentration of the products reaches a certain level, the reverse reaction is going to begin to occur. Equilibrium is said to be established when the rate of the forward reaction matches the rate of the reverse reaction. At this stage, the concentrations of both reactants and products are going to stabilize and remain unchanged. Consider the analogy of climbing up an escalator that is moving downwards. If your speed matches that downward speed of the escalator, you are going to remain in the same place. Despite your best efforts to ascend, that escalator's downward trajectory is going to keep you stationary. So equilibrium can be classified in two categories: static and dynamic. Static equilibrium occurs when there is no exchange between the reactants and the products, effectively meaning that the reaction is in a state of rest, with both forward and reverse reaction rates being zero. An illustration of static equilibrium is the transformation of carbon from graphite to diamond. Although this reaction can reverse, it stabilizes at a juncture where it ceases to progress further without the application of significant energy or pressure. For instance, diamonds require being heated to 200 degrees Celsius to revert back to graphite. Thus, at standard room temperature, no conversion between diamond and graphite is going to occur. This scenario exemplifies static equilibrium, where the rates of both the forward and the reverse reactions are non-existent. They're just static. And then we have dynamic equilibrium. This occurs when the rate of reactants transforming into products is matched by the rate of products reverting into reactants, with these conversions occurring continuously within the system. A great example of this is a sealed bottle of carbonated soda. This is going to provide a practical example when it comes to dynamic equilibrium. So with soda, the rate at which carbon dioxide gas escapes the liquid is precisely balanced by the rate in which it dissolves back into the liquid, making it a dynamic equilibrium. So water is truly a remarkable molecule. It's not just an essential when it comes to life, but it's because of its unique properties that makes it crucial for biological functions. One of the key features when it comes to water is its structure and polarity. Water molecules are shaped in such a way that oxygen atoms, which are highly electronegative, tends to attract more electrons towards itself compared to the hydrogen ions that it's bonded with. Oxygen and hydrogen form covalent bonds. As we discussed in our atomic structure video, oxygen with an atomic number of 8 has 8 protons and 8 electrons, 2 in its inner shell and 6 in its outer shell. It needs 2 more electrons to complete its outer shell based on that octet rule. It gets these electrons when 2 hydrogen atoms, which both have 1 valence electron in the outer shell, share with oxygen. This uneven distribution of electrons gives oxygen a slightly more negative charge and hydrogens a slightly more positive charge. This polarity allows water molecules to easily bond with each other. The slightly negative oxygen of one molecule can attract the slightly positive hydrogen of another, forming a hydrogen bond. These bonds are what gives water its special properties, such as its ability to dissolve many substances, its surface tension, and its relatively high boiling point compared to other molecules of similar size. Have you ever observed how water sticks to the side of a glass and wondered, how does water stick to a glass without falling down? Does it defy gravity? What's particularly interesting about water is its ability to adhere to the walls or surfaces of objects, a phenomenon known as adhesion, which assists in countering gravity's pull. Furthermore, water molecules form hydrogen bonds amongst themselves. This process is called cohesion. For this, I want you to picture water droplets on a waxed car's surface. They tend to bead up because they prefer sticking to each other rather than spreading out all over the surface of the car. Additionally, cohesion explains why water striders, those little bugs, which are my favorite insects by the way, can effortlessly move across the surface of a pond or a stream without actually having to go into the water. This is because cohesion enhances the surface tension of water, enabling these little bugs to skate across it without sinking. So here's the key difference between these two concepts. When it comes to adhesion, we have water molecules that are attracted to dissimilar objects, meaning they're attracted to something else besides themselves. Whereas with cohesion, their attraction is going to take place between the water molecules themselves. So cohesion, they're going to be co-working together. That's your memory trick, co-worker, co-home. They like to stick to each other, right? They're at home when they're with each other. Whereas adhesion is they're sticking to dissimilar things that are not water. So I like to think of it as adhesive tape, where water molecules are like sticky objects like we see with adhesive tapes when it comes to sticking to walls or different surfaces. So let's talk about another important concept when it comes to the T's, and that is solute, solvent, and solutions. So let's begin by exploring what constitutes a solution with a simple experiment involving 3 different glasses of water. In the first glass, we're going to add salt. In our second glass, we're going to add sugar. And in our third glass, we're going to add pebbles. After allowing some time for these examples to interact with water, we're going to observe the following. The salt is going to completely dissolve, forming what we know as a homogeneous mixture. This means that the mixture is going to have a uniform composition, and with looking with just our naked eye, we're not going to be able to differentiate between the salt particles and the water. Just like with our salt, sugar is also going to dissolve completely in the water, resulting in another homogeneous mixture. We're also not going to be able to differentiate between the sugar particles and the water itself. So again, it's going to have a uniform composition. However, unlike salt and sugar, the sand or pebbles that we put in our last water is not going to dissolve. This results in what we know as a heterogeneous mixture, where the individual particles of sand or pebbles are going to remain visible and distinct from the water. From these observations, we can conclude that both the salt water and sugar water mixtures are solutions because they consist of substances, both salt and sugar, that are soluble in water, forming homogeneous mixtures. On the other hand, the mixture of pebbles and water is not a solution due to its heterogeneous nature, in which the substances remain visible to the eye. Thus, a solution is defined as a homogeneous mixture of one or more solutes where the components are completely dissolved in a solvent, leaving no visible trace of separation to the naked eye. So here are some common examples of solutions to illustrate this concept. When we're looking at cold drinks, we have a combination of carbon dioxide, sugar, flavors, as well as water. When mixed together, they form a homogeneous mixture. This means all components are evenly distributed throughout the drink, making it a solution. In the case of fog and clouds, water vapors are dissolved in air, making it a homogeneous mixture. And lastly, when alcohol is mixed into water, it dissolves completely, resulting in our last homogeneous mixture. The uniform distribution of alcohol molecules within the water makes us a classic example of a solution. All three of these examples represent solutions where the solute is completely dissolved in the solvent, creating a uniform mixture without any visible separation of components. Let's delve into solutes and solvents by examining a salt solution and a sugar solution. In both cases, these solutions consist of two components, salt and water in the salt solution, and sugar and water in the sugar solution. As we discussed before, both salt and sugar can be dissolved in water and present in smaller quantities compared to the water itself. Therefore, we define a solute as a component of a solution that can be dissolved and is present in smaller amounts. Conversely, a solvent is defined as its ability to dissolve substances and is present in larger amounts. So this makes sense in our example, right? We have both salt and sugar, which are smaller amounts, making them our solutes, and both water in both cases is going to be our solvent because it's going to be present in larger amounts. An easy way to remember the differences is sugar water syrup, where our solute is sugar, our solvent is water, and our solution is syrup. It's also easy to recall that as we move down our list of definitions, our number of characters in each word is going to increase. Solute has 6 characters, solvent has 7 characters, and solution has 8. Here are some more common examples of solutes and solvents. In a vinegar solution, we can see that acetic acid is going to be our solute, it's a much smaller number, and our water is going to be our solvent because it's in greater quantity. Moving down the line, we have sugar and milk. Sugar is going to be our solute, and milk is going to be our solvent. And then with alcohol and water, again, alcohol is going to be our solute, and water is going to be our solvent. If you haven't been able to pick up on it yet, water is often hailed as the universal solvent because of its exceptional ability to dissolve a wide variety of substances, particularly polar substances. Polar substances such as salt, which is sodium chloride, and sugar, which is sucrose, dissolve well in water. This is due to the partial charges on their molecules, which attract the partial charges on water molecules, thus facilitating dissolution. Conversely, we have non-polar substances like we see with oils and fats, which often struggle to dissolve in water. Their molecules lack charged regions, which are necessary to effectively interact with water molecules. Therefore, although water can dissolve numerous types of substances, it is predominantly effective with polar substances, earning its reputation as the universal solvent. Additionally, when preparing for your ATI TEAS, you're going to come across 2 important terms, hydrophilic and hydrophobic. Hydrophobic means water-fearing or water-hating, and it describes substances that do not dissolve well in water and tend to repel it. This category includes oils, fats, as well as other nonpolar molecules. Examples of hydrophobic materials in daily use could be waterproof fabrics, which are treated to repel water. Hydrophilic means water-loving, and it refers to substances that dissolve readily in water. This includes polar substances and molecules like ionic compounds such as salt and polar molecules such as alcohol. Many beverage ingredients are hydrophilic, allowing them to dissolve in water. Because water itself is a polar molecule, hydrophilic substances can disintegrate and become encased in water molecules, which aids in their dissolution. So let's discuss molarity, a term frequently used when discussing solutions. We often refer to a substance's concentration rather than simply counting its moles. The concentration tells us the number of moles of a substance present per unit of volume. The unit of measure for concentration in molarity is expressed as moles of a solute per liter of solution and is denoted by the capital M. For instance, a solution with a molarity of 2M contains 2 moles of solute for every liter of solution. We can change the concentration of a solution through the process of dilution, which involves adding more solvent to the solution. As a result, if the number of moles of solute remains constant, then the solution becomes less concentrated because of the overall volume increase. To calculate the new concentration after dilution, we use a specific calculation that requires the initial concentration, the initial volume, and the final volume to which the solution will be diluted. These quantities are inversely related, meaning that if you double the volume of the solution, the concentration will be halved. So let's take a look at an example. We have calculate the molarity of a solution prepared by dissolving 9.8 moles of a solid NaOH in enough water to make 3.62 liters of solution. So we know what our moles are, and we know what our solution is in liters, so we just go ahead and we plug that into our molarity equation. So we have M is equal to 9.8 moles over 3.62 liters, and we're just going to divide. And that's going to give us a molarity of 2.7 moles per liter. So let's take a look at a more complex problem. So we have 0.850 liters in a 5M solution of sodium chloride is diluted to a volume of 1.8 liters. So we have our original volume and our new volume here with water. What is the concentration of the diluted solution? So we start with our equation. We have M1 multiplied by V1 is equal to M2 multiplied by V2. So that's just your first moles, your first volume, your second moles, your second volume. So here we need to figure out what our second moles is if we dilute the solution with 1.8 liters. So I'm going to go ahead and put that on the left side of my equal sign, and I'm going to multiply my first solution, which is our M1 V1, and I'm going to divide that by what we added for the dilution of our second solution. So we're just going to go ahead and plug in our numbers. So we have 5M is multiplied by 0.85 liters. This is our first solution. And it's going to be divided by what we have added to dilute the solution of 1.80 liters. If we do our calculations correctly, we should see that the molarity, the moles that we see in our second solution, is now going to be 2.36 moles. Osmosis is a term that is often mentioned, but can be quite complex to grasp. However, understanding it can clarify numerous important questions that you may have, such as, why is it harmful to administer an IV of pure water? Or what happens when a saltwater fish is placed in fresh water? We'll explore the answers to these questions while explaining the process of osmosis. When we're discussing osmosis, we're referring to how water molecules move through a semi-permeable membrane such as a cell membrane. Due to their small size, water molecules can pass through the membrane unaided. Or if we have a large quantity of water molecules, they can move through a specialized protein channel known as an aquaporin. This transport of water molecules across the cell membrane is considered a passive transport, meaning that it doesn't require any energy in order to get across. Water molecules naturally migrate from areas where their concentration is high to where their concentration is low. Another way to consider this movement is to consider solute concentration, a region where a low water concentration generally means that we're going to see a higher concentration of solutes like salt and sugars. Since these solutes are dissolved in a solvent like water, the water will tend to move towards areas with higher solute concentrations, which correspondingly have lower water concentrations. Thus, if you're trying to predict the direction of water molecules in osmosis, simply look for concentrations that have greater solutes. In the absence of other influences like pressure, water is going to continuously move towards the area of higher solute concentrations. An easy way that I like to remember osmosis is to think of H2O and O in osmosis. This means that it's going to be the movement of water. So let's introduce what is known as the U-tube setup. Yes, it's a little bit like YouTube the platform, but it's a little bit more scientific. In the middle of our U-tube, we're going to have semi-permeable membranes, similar to a cell membrane which allows small water molecules to pass through, but blocks large molecules like salt. Initially, when we take a look at our first example, we can see that both side A and side B are filled with equal levels of water. While it may appear nothing is happening, water molecules are constantly in motion. However, the net movement between the two sides is zero, meaning there's no overall change in the direction of the water movement. So let's add a twist. Suppose we add a significant amount of salt to side B. Given what we know about osmosis, in which direction do you think the water is going to move? Side A or side B? And you're absolutely correct. It is side B. Side B now has a higher solute concentration compared to side A. Water naturally moves towards area with higher solute concentrations, which also means that we're going to see a lower water concentration on that side. Consequently, the water level on side B is going to rise as water attempts to move to dilute and equalize that concentration on both sides. Once equilibrium is achieved, that net movement of water across the membrane will stop, yet the water molecules will continue to move back and forth dynamically. This continuant movement reflects the natural kinetic behavior of water molecules, always seeking to balance and redistribute themselves. Here's a key term that you're going to need to remember. Side B is going to be described as hypertonic. This means that it has a higher solute concentration. However, it's important to note that calling something hypertonic always involves a comparison. So in this case, we can say that side B is hypertonic relative to side A because it contains more solutes than we see in side A. We can also refer to side A as hypotonic. The mnemonic hypo rhymes with low, hypo-low, and this can help you remember hypotonic areas having a lower solute concentration compared to their counterparts. So now let's apply these concepts beyond the U-tube experiment and into more real-life practical scenarios. When someone receives an IV at a hospital, the fluid in the IV might appear to be pure water, but in reality, it's definitely not. Using pure water would be extremely harmful because of osmosis. Let's consider why. Let's imagine that hypothetically the pure water was used in an IV. This IV tube typically runs into the vein, providing direct access to the bloodstream, which is crucial for medication administration. Your blood contains various components, including red blood cells. Now let's consider solute concentrations. Between the hypothetical pure water of an IV and your red blood cells, which one has the higher solute concentration? Since cells are not empty but do contain various solutes and the hypothetical pure water has none, the solute concentration inside the red blood cell is going to be higher. Due to osmosis, water moves from the low solute concentration in the IV, which we see with pure water, towards the higher concentration inside of our cells. As a result, the red blood cells, which are hypertonic compared to the pure water, is going to rush into this cell and it's going to cause that cell to start to swell and become full of water and potentially even bursting, which could be really bad for the organism. When a person requires hydration through an IV, they're usually given a solution that is isotonic to their body and their plasma. Isotonic means that the solution is equal in concentrations of solutes to the plasma, preventing that osmotic imbalance. Therefore, there will be no swelling or shrinking of red blood cells, ensuring their normal function is maintained. Hypertonic means that these solutions have higher concentrations of solutes compared to another solution. An easy way that I like to remember this is hyper rhymes with higher, hyper, higher. Because there's going to be a higher solute imbalance when it comes to hypertonic solutions, we're going to see water coming out of our red blood cells. Because its outside environment solutes are going to be greater than the solutes found within the cells. So as we know with osmosis, the water is going to go from a lower concentration to a higher concentration in order to even it out. So you're going to see cells shrinking whenever we're talking about hypertonic solution because of that lack of water. Conversely, hypotonic solution refers to a lower concentration of solutes compared to other solutions. And an easy way that I like to remember this is hypo means low. It rhymes and it makes it easy to remember. So because the solution has less solutes than we're going to find inside of our red blood cells, the same thing is going to happen with osmosis. It's going to want to move towards these cells with a higher concentration. And because of this, it's going to cause the red blood cells to ultimately swell up and potentially burst depending on how imbalanced those solutes are. So when you're trying to figure out which kind of solution is isotonic, hypertonic, or hypotonic, this is an easy way that I like to remember it. The two solutions that you're going to see commonly with isotonic is going to be your normal saline, 0.9%, as well as your lactated ringers. If you're looking at hypertonic, hyper meaning higher, you're going to see a lot higher numbers. You're going to see 3% to 5% saline, 10% dextrose and water, 5% dextrose in normal saline or half normal saline. You're going to even see 5% dextrose in lactated ringers. So you're going to see higher percentages, meaning that there's higher solutes. In contrast, where we're talking about hypotonic solution, hypo meaning low, you're going to see lower concentrations, right? So you're going to see half normal saline. You're going to see 0.225% normal saline and 0.33% normal saline. Next up, let's talk about diffusion, which refers to the process where the net movement of a substance moves down its concentration gradient, traveling from an area of high concentration to one of a low concentration. So the big key difference here when we compare to osmosis is referring to the water. We're talking about the solvent, whereas now we're talking about the movement of particles, not the movement of water. So we're talking about the solutes. So that's why it's going to be a little bit different from what we were talking about with osmosis. What's important to note that this process isn't limited to liquids. It can also refer to gases, such as air fresheners when they're sprayed up into the air. The molecules of an air freshener spread from where they are most concentrated to where they are less concentrated, allowing the scent to be detected even from a distance. Let's also delve into some key points when it comes to diffusion. The first term being net movement, which refers to the overall direction of the molecule movement. Diffusion doesn't prevent molecules from moving in the opposite direction, nor does it imply that the molecular movement ceases altogether. Even when equilibrium is reached, where the concentration of molecules is equal throughout the space, the molecules continue to move around, just like we saw with osmosis. Secondly, diffusion is a type of passive transport, meaning that it doesn't require any external energy to occur. Molecules move due to the inherent potential energy present in the concentration gradient itself. This is why the diffusion of a substance like oxygen into cells is considered passive transport. No additional energy is required for this to happen. Passive transport is distinct from processes like active transport, which requires energy input. Before we move on to that, we have one specific type of diffusion known as facilitated diffusion. This process still involves the net movement of molecules from an area of higher concentration to an area of lower concentration. However, certain molecules may be too large or possess other characteristics that prevent them from crossing the cell membrane itself. In such cases, these molecules have to pass through a protein channel. This is still considered diffusion because it's a form of passive transport and the molecules continue to move along their concentration gradient. The key difference is that facilitated diffusion requires the presence of a protein channel to assist the molecule in entering the cell. Let's talk about several factors that can influence the rate of diffusion. So number one, we have distance. So the further the molecule has to travel, the slower the diffusion rate. For instance, diffusion might occur at different rates in 5 feet compared to 5 miles, due to the increased distance the molecule must travel. Next up, we have temperature. So quick question, do you think a higher or lower temperature would increase the diffusion rate, assuming all other factors are going to remain the same? You're right, generally higher temperatures are going to increase the diffusion rate. This is because the molecules move more rapidly at higher temperatures, enhancing their energy, which in turn speeds up diffusion. Next up, we have solvent characteristics, which just means that the density of a solvent can also impact diffusion. The denser a solvent is might impede molecular movement, thereby reducing the diffusion rate. And then we have traveling characteristics. Not all entities involved in diffusion are strictly molecules. There can be other types of substances as well. For example, the mass of a diffusing substance plays a critical role. Typically, substances with greater masses diffuse slower than those with less mass due to their inertia. And then lastly, we have barrier characteristics. If a diffusion involves crossing a barrier, such as a cell membrane, the nature of the barrier significantly affects the rate of diffusion. Small nonpolar substances generally pass through cell membranes more easily than those with larger, more polar substances, influencing the overall rate of diffusion. So we talked about passive transportation when it comes to diffusion, facilitated diffusion, and osmosis. You should know one more additional mode of transport when it comes to the ATI TEAS, and that is active transport. Active transport is a critical cellular process where molecules are transported against their concentration gradient, moving from areas of lower concentration to areas of higher concentration. Unlike passive transport, which allows molecules to move along the gradient without using energy, active transport requires the cells to expend that energy in order to make that happen. This energy is typically provided in the form of ATP, also known as adenosine triphosphate, the cell's primary energy currency. In active transport, cells use specialized protein channels embedded in the cell's membrane known as transporters or pumps. These proteins bind to the molecules they are designed to transport, changing shape with the energy derived from ATP to move these molecules across the cell membrane. This process is vital for maintaining essential functions such as nutrient uptake, waste removal, and ion balance within the cell. Active transport is not only crucial when it comes to individual cells, it is also pivotal when it comes to physiological processes across organisms. For example, it helps with the accumulation of nutrients across a concentration gradient like we see in our intestines, and with the reabsorption of ions that we see within our kidneys. By understanding active transport, researchers and medical professionals can better comprehend cellular and systemic functions, potentially leading to improved treatments for various health conditions where transport processes can be disrupted. So let's explore the pH scale and the nature of acids and alkalines. The pH scale that we use is used to determine whether a solution is acidic or alkaline, ranging anywhere from 0 all the way up to 14. The lower numbers that we see, getting all the way closer to 0, they're going to be more highly acidic, while the higher numbers that we see, getting closer to 14, is going to signify high alkalines. A substance is considered neutral if it has a pH of 7, just like we see with pure water, which is neither acidic nor alkaline. To put this into perspective, let's consider the acid that we find in our stomach, which has a pH of around 2. This acidity helps kill bacteria and aid in our digestion. On the other hand, we have acid range, which typically has a pH of 4, indicating that it's less acidic than stomach acid, but it's still harmful to our environment. Moving to our alkalines, common household items provide good examples. So when we look at body wash typically has a pH of around 9, making it kind of mildly alkaline. Well, when we look at bleach actually has a pH closer to 12, indicating that it has a very strong alkaline. I want you to keep in mind that examples like these are provided to help conceptualize the pH scale. You don't have to memorize these specifically when it comes to your ATI TEAS. So pH can be measured using several methods, each with its own advantages. One common method involves the use of indicators, which are chemicals that change color based on the pH level of the solution that they're in. These indicators are typically dyes that respond to the specific pH levels, making them useful for visual assessments of acidity and alkalinity. Some indicators are composed of a mixture of dyes and are known as wide range indicators because they can gradually change color across a broad spectrum of pH values. A well-known example of a wide-range indicator is a universal indicator, which displays a color range from deep red in very acidic conditions and blue or purple in highly alkaline conditions. Litmus is a commonly tested thing that you will see on the TEAS whenever it comes to pH balance, because it is an indicator commonly found absorbed onto paper as litmus paper. So this is important to memorize. Whenever we have blue litmus paper, it's going to turn red under acidic conditions, meaning that the pH is going to be less than 7. And in contrast, red litmus paper is going to turn blue under alkaline conditions whenever we have a pH that is greater than 7. Another method for measuring pH is known as a pH probe that is attached to a pH meter. This particular technique involves inserting a probe into a solution to electronically determine its pH levels. The meter's digital display on the front of the screen is going to provide a precise numerical reading. So the advantage to using a pH probe over other indicators is its accuracy and precision, as it eliminates that subjectivity when it comes to interpreting color changes. So next up, let's clarify what classifies a substance as an acid. So an acid can be defined as any substance that when it dissolves in water forms a solution with a pH of less than 7. This acidic characteristic is due to the release of hydrogen ions into the water, making the solution more acidic. An example of this is when we put hydrochloric acid, also known as HCl, into water, it's going to dissolve. And what it does is it disassociates and releases hydrogen ions, thus increasing the hydrogen ion concentration that we would see in the solution. On the other hand, bases are substances with a pH greater than 7. Within the category of bases, there are specific subgroups known as alkalines. Alkalines are bases that are soluble in water. When an alkaline dissolves in water, they produce hydroxide ions, also known as OH negative, contributing to the solution's basic nature. A great example of this would be sodium hydroxide, also known as NaOH, which when dissolved in water disassociates into sodium, Na positive, and OH negative ions. The OH negative ions can combine with hydrogen ions in the water to form H2O, effectively reducing the concentration of hydrogen ions. When acids and bases are mixed together, they undergo a neutralization reaction. This reaction typically results in the formation of water as well as salt, effectively neutralizing the original substance's acid and basic properties. For instance, when hydrochloric acid reacts to sodium hydroxide, which is commonly used as an acid and base reaction, respectively, they're going to produce sodium chloride as well as water. These neutralization reactions can also be represented at the ionic level, where hydrogen ions from the acid and OH negative ions from the base combine to form water. Since both acids and base neutralize each other, the pH of the resulting products are typically neutral, around a pH of 7. Before we move on to our practice questions, let's review some common acids and bases that you might encounter on the TEAS. Prominent acids that you might see would be hydrochloric acid, sulfuric acid, and nitric acid. The big key memory trick that I want you to take away is that a lot of these acids end in IC, like we see in hydrochloric, sulfuric, and nitric. On the base side, you're frequently going to come across hydroxide and carbonates, which means that they are going to end in oxide or nates, like we see in sodium hydroxide and calcium carbonate. So our question states, what type of ions do alkalis produce in water? Is it hydrogen ions, hydroxide ions, bicarbonate ions, or sulfate ions? And the correct answer is hydroxide ions. It's going to be B, because alkalis is a subset of basis, and when it dissolves in water, it's going to produce hydroxide ions contributing to its basic nature. What is the primary function of a wide-range pH indicator in a laboratory? Is it to determine the exact pH value of a solution? Is it to determine general estimate of the pH range of a solution? Is it to neutralize acids and bases, or is it to increase the reaction rate? And the correct answer is B, to provide a general estimate of the pH range of a solution. Remember, wide-range pH indicators are used to give a visual approximation of the pH value across a broad range, helping to identify whether a solution is strongly acidic, neutral, or strongly basic. What does a pH of 7 indicate about a solution? Is it acidic, basic, neutral, or highly reactive? And the correct answer is C, it is neutral. Remember, a pH of 7 is considered neutral, indicating that that solution is neither acidic or basic. And we see this a lot when it comes to pure water. What is formed when an acid reacts to a base? Is it acid only, base only, salt and water, or hydrogen gas? And the correct answer is C, salt and water. Remember that neutralization reaction, that reaction between an acid and a base, is known as neutralization reactions, and they typically are going to produce salt and water. I don't know about you, but after all that chemistry talk, I'm feeling a little bit different. As always, if you have any additional questions, make sure that you leave them down below. I love answering your questions. Head over to nursecheungstore.com where there's a ton of additional resources in order to help you ace those ATI TEAS exams. And as always, I'm going to catch you in the next video. Bye!